This is the Chapter 8 video, Part 3. In this video, we're going to look at Section 8.3, which looks at constructing a confidence interval to estimate a population mean. So starting off here, we have the basic steps for calculating a confidence interval. These are review from the previous section, where in the previous section, we looked at calculating the confidence interval for a population proportion. And so you'll notice these exact same basic steps are on page 13 of the notes. Looking through these, we can see that our basic steps are to check our assumptions, calculate our statistic, calculate our margin of error, which consists of the critical value and the standard error, put them together to get our confidence interval, and then interpret our confidence interval in context. When we work with a mean, the critical value will come from a standard normal distribution if we know the population standard deviation sigma. But most of the time we do not know sigma, and we need to estimate it with the sample standard deviation. And recall that the sample standard deviation is denoted by the letter S. When we have a sample standard deviation, the critical value needs to come from what is known as a t-distribution. So we're not going to work with the standard normal for means, we're going to work with the t-distribution. Similar to a standard normal distribution, all t-distributions are centered at 0. Instead of defining a t-distribution by a mean and standard deviation, we define it by what is known as degrees of freedom. Degrees of freedom are calculated based on the sample size. The higher the degrees of freedom, the closer the t-distribution becomes to a standard normal. So looking here in the picture, we have a couple different t-distributions. What you'll see here is this top curve represents the z-distribution, or your standard normal. These are two different t-distributions. This t-distribution has an n close to 30, and this one has an n smaller than 30. When the critical value originates from a t-distribution, we denote it by t star. So notice we no longer have z star, we now have t star. But we find the t star very similar to how we found the t star for a normal distribution, or probably the z star for a standard normal distribution. We start by drawing the t-distribution, we shade the middle p% of the curve, and we find the positive endpoint. This will be the value of t star. So what we have on the next page are some pictures from StatKey. When you go into StatKey, you can create a t-distribution just like you did the normal distribution. So instead of looking for the theoretical normal button, you'll look right next to it for the t button. So for example, if I wanted to find the critical value for a 99% confidence interval, and suppose I had a t-distribution with 30 degrees of freedom, here's how we could do this. You would go to StatKey, you would click on t to the right of theoretical distributions. Type in 30, because StatKey is automatically going to ask you for the degrees of freedom. This will create a t-distribution with 30 degrees of freedom. You click on the two-tail option, so here in the picture, that's right here, and then you're going to change the value in the center to be 99. Notice, here is the endpoint. And so that positive endpoint gives the critical value, or in this example, t star would be equal to 2.750. You could also find critical values using what is known as a t-table. You can find a copy of the table at this link at the top of the notes, and then there's 2 additional videos for you to watch. The first video goes through step-by-step on how to find t star using StatKey. The second video goes through how to use the t-table to find t star. And so when you click on that, you want to already have your t-table ready. Here's what it looks like, and I got this by following that link at the top of the page. And this video will walk you through step-by-step how to read that t-table. Alright, so now that we've got our generic steps for finding that confidence interval, and we've seen how to find our new critical value, now we can go through the steps for how to calculate a confidence interval for a single population mean. So notice the mean that we're interested in now is mu. So mu is our population mean. To use the formula for the confidence interval, we first need to confirm that the sample size requirement for the central limit theorem is satisfied. For a single mean, the sample size requirement we need to check is that the population data is reasonably normal or n is bigger than or equal to 30. And then additionally, just like before, we need a random sample. From here, our steps are very similar to before. We'll find our statistic, which in this case is x bar. Our margin of error will still be the critical value times the standard error. The difference now is that the critical value is a t star, where t star comes from a t-distribution with n minus 1 degrees of freedom. And so n here is your sample size. And then now we have a new formula for standard error that is s divided by the square root of n. Combining the above, we have the following formula for a confidence interval for a single mean. And then the last thing we'll need to do is interpret that interval. And remember, those intervals will always, the interpretations will always include three things: the level of confidence, we're going to reference our parameter in context, and then we're going to give the calculated interval. Here we have a fully worked solution. Let's go through all the steps. So we want to rent an unfurnished one-bedroom apartment in Richmond, Kentucky next year. The mean monthly rent for a simple random sample of 45 apartments advertised in the Richmond Register is $1,125, and the standard deviation of the sample is 225. You decide to calculate a 99% confidence interval to get an idea of how much you will spend per month. So first we'll start with our sample size check, and remember, really we could write this as assumptions. So we've got assumptions. There are 45 apartments in the sample. The sample size is at least 30, so the requirements are satisfied. And then additionally, we have a random sample. And we know that because they tell us it's a random sample of apartments. Next, we need to calculate the statistic. We'll notice that they tell us that the sample mean was 1,125, so this tells me that x bar is equal to 125. Next, we need to find the critical value. Our critical value comes from a t-distribution with n minus 1. In this case, that would be 45 minus 1 degrees of freedom. So using the t-table, we'll have this value. So let's review how to do that. So looking at our t-table, which is here, notice that the left-hand column has the different degrees of freedom. So we need degrees of freedom 44. Notice that 44 is not on the table. Whenever the value you need is not on the table, you'll round down to the value that is on the table. So 44 falls between 40 and 60, so we always round down, and so we'll be here on the 40 row. So looking at the 40 row, I now need to decide which column I need. Well, I need 99 degrees of freedom. So one way we could do that is looking up here at the top, we could look at the two-tail column. And what we're going to do is we're going to look for the value that would be left over if we subtracted our level of confidence from 1. So if I'm 99% or 0.99 confident, 1 minus that value would leave me left over with 0.01. Seeing where those match up, give me the value of 2.704. And so if we go back to the notes, we see the value that we have here is 2.704. Next, we need to calculate our standard error. Here is our formula. S is our sample standard deviation, and n is our sample size. In the problem, we're told that the standard deviation of the sample was 225, so we have 225, and there were 45 apartments in the sample. Placing this in your calculator gives 33.5401. Next, we can combine the above into the confidence interval for a single, and this should say mean. So we have x bar plus or minus t star times s divided by the square root of n. Plugging in our x bar that we have all the way from up at the top is here. Here we have our t-star that we found here, and here we have our standard error that we found here. Multiplying these two numbers together gives 90.6924. So we have 1,125 plus or minus this value, which results in this interval. And again, any number inside this interval is a reasonable value for the parameter. Now we interpret our interval in context. So we start out with our level of confidence. We are 99% confident. We then reference our parameter, that the average rent for an unfurnished one-bedroom apartment in Richmond, Kentucky is, and then we give the interval we found. Let's try some practice problems together. How much of a typical person's day is spent in front of the TV? A recent general social survey asked respondents, on the average day, about how many hours do you personally watch television? A computer printout from Minitab summarized the results. So here we have our summary. We see that the sample size was 1,098. We can see that from right here with the in. Pardon me. We can see that right here. The sample mean was 309. They're rounding this value right here. The sample standard deviation was 2.87. Again, they're rounding this value right here. And the standard error of the mean was 0.08. So they're rounding this value right here. And the 95% confidence interval is given right here. So let's answer some questions. What do the sample mean and sample standard deviation suggest about the likely shape of the population distribution? So, starting with part A. Recall that if the population distribution is normal, then approximately 99% of the values will fall within 3 standard deviations of the mean. And this comes from the empirical rule that we saw in earlier notes. Okay, so let's see what this would suggest. So our mean, using our computer output, is equal to 3.09, and the standard deviation is equal to 2.87. So let's look at the mean plus or minus 3 times the standard deviation. So notice this is not a confidence interval. Here we're just applying the empirical rule to our population data. So if we take 3.09 and we subtract away from it 3 times 2.87, I get negative 5.52 all the way up to 11.7. So this suggests that if I looked at how much time the typical person's day is spent in front of the TV, then those values for the amounts that these people are reporting will fall between negative 5.52 hours and 11.7 hours if the population distribution is normal. Well, it doesn't make sense for people to watch negative amounts of TV, so this suggests that the population is not normal. Because if it were normal, then we would be able to talk about the majority of the values falling between these two. and that doesn't make sense. So realistically, the population distribution is probably right skewed. We wouldn't think it would be left skewed because then we would still be getting negative numbers. So more than likely what happens, if we think of the number of hours people watch, there's probably some people at 0, kind of peaks up a little bit, and then we'll have some of those extremes causing that right tail. All right, B. How did the software get the standard error, and what does it mean? So B, we have a formula for our standard error. Remember that that's equal to our sample size divided by the square root, that's equal to the sample standard deviation divided by the square root of our sample size. Filling in these values, our sample standard deviation was 2.8651 divided by the square root of our sample size, which is 1,298. We'll place that in the calculator. This gives the value 0.07952, which you'll notice is exactly the value they got right here. And so what does this mean? This value, this standard error, this is the standard deviation of X bars taken from different random samples. In part C, we need to interpret the 95% confidence interval reported by the survey. So we'll start out with our level of confidence. We are 95% confident. Next, we're going to reference our parameter in context that the mean number of hours a typical person spins in front of the TV is, and then we're going to give our interval between, and again, the interval we're referencing is the confidence interval given to us in the output, 2.93 and 3.24 hours. All right, let's look at another example. So here, we're going to look at an example of what computer output would look like. So how do we interpret computer output for a confidence interval? So in the previous page, we looked at some computer output, but it was somewhat shortened. So here we're going to look at a larger piece of output. There are many computer programs and online applets that will calculate confidence intervals for you. Sometimes the output will explicitly give you the interval. Other times the output will give you the summary statistics so you can calculate the interval. The format of the output will vary from program to program. Below is a sample of what the output may look like for a single mean. And even though the output varies a little bit from software to software, they will be fairly similar. Notice what we have here is the same piece of computer output, and I've copied and pasted it 4 different times. And so what we're going to do is look at what each of the pieces of the output you need to be aware of. So the first one is sample size. Software sometimes uses capital N instead of little n to denote the sample size. And so for this output, the sample size was 55. The mean is usually denoted as the mean. So the mean of this sample would be 101.13. For proportions, you would see the word proportion or percentage here in computer output. Standard error mean. SE mean stands for standard error of the mean. For proportions, you may just see SE or SE proportion. So for this example, the standard error of the mean is equal to 1.7057. So recall, when we're talking about standard error, we're talking about taking S divided by the square root of it. So notice here, we have the standard deviation, which we're going to get below. The standard deviation of the sample is 12.65. If we divide that by our sample size, or the square root of our sample size, putting that in our calculator, gives us 1.7057, the exact value that they got right here. So this is how you could go about reading computer output to get the same information that you could calculate by hand. If the population is not normal, is the method robust? And so recall, in our assumptions, we could either have that the population was normal or a large enough sample size. So one of the basic assumptions for the confidence interval using the t-distribution is that the population is normal. If we were to only rely on that, it would be problematic since many variables have distributions very different than the normal bell shape. But for large enough sample size, this is no problem at all because of the results from the central limit theorem. So this is why we keep on checking in our assumptions that n is bigger than or equal to 30 when working with the sample mean. But what about when we have a small sample size? Fortunately, the confidence interval using the t-distribution is robust in terms of the normality assumption. So what does robust mean? A statistical method is said to be robust with respect to a particular assumption if it performs adequately even when that assumption is modestly violated. So even if the population distribution is not normal, confidence intervals using t-scores work very well and works increasingly well as that sample size increases. So again, this is why we're looking for that n bigger than or equal to 30. An important case in when t confidence intervals does not work well is when the data contains extreme outliers. So if we have extreme outliers, it makes it very important we have these large sample sizes. Another case is that the t-distribution does not work well with binary data or proportions. So notice when we first worked for proportions in this chapter, we didn't use the t-distribution, we used that standard normal. All right, so next in section 8.8, we're going to talk about choosing a sample size for a study. So how does a poll or study know just how large a sample is needed to reach their desired results? This sample size depends on how much precision is needed. This is measured by the margin of error with a particular confidence level. What factors affect the choice of sample size? The desired precision, confidence level, variability of the data, and cost. So note, when selecting sample size, it's imperative you always round any non-integer value up to the next integer. Let's think about why. If a formula tells us that we need, for instance, a sample size of 84.3 people, cats, dogs, plants, etc., this means that 84 is not large enough. We cannot sample 3/10 of a person, that should say person, not parson, or other item. Therefore, a whole number must be reported. We would say that the sample size needed is 85. This would still be true if the formula resulted in 84.0001. So let's look at several examples of this. So how can we determine the sample size needed to obtain a desired margin of error? Sometimes we want to create a confidence interval where the margin of error is a specific size. To have the margin of error a pre-specified size, we need to know what sample size to take. You can choose your sample size in advance depending on your desired margin of error. The formula for sample size will depend on whether you're working with a single mean or a single proportion. So we're going to start out by looking at the sample size formula for a single proportion. Notice, for a single proportion, the formula for the margin of error is as follows. So recall that our margin of error is equal to our critical value times our standard error. Solving for n, we have the following. So n is equal to z star divided by the margin of error squared p hat times 1 minus p hat. This formula requires that we know p hat, but since we do not have a sample yet, we do not know p hat. So instead, we'll write that n is approximately equal to this value. We always round n up to the nearest whole number to find the minimum sample size required. If we compute n and come up with a small sample size, we should go back and be more demanding by either having a smaller margin of error or higher level of confidence. So how do we estimate the p-hat that we need to plug into here? There are two different options. We could use the statistic p-hat from a previous study or similar population, or set p-hat equal to 0.5. So let's look at two examples. Suppose we want to estimate a proportion with margin of error equal to 0.05 with 90% confidence. A previous study found the confidence interval 0.6 to 0.8. How large a sample size do we need? We are given that the margin of error is equal to 0.05 here. Also, we know for a 90% confidence interval, using those common values on page 13 of the notes, z star is equal to 1.645, since we want that 90% confidence interval. The previous study found the confidence interval of 0.6 to 0.8, therefore the statistic from the previous study was 0.7, because remember that the statistic is at the center of the confidence interval. Using the information from the previous study, we're going to set p-hat equal to 0.7. So here we fill in the formula. Notice this is 227.31. We always round our sample size calculations up. So this suggests we need a sample size of at least 228. Looking at another example, most online polls calculate 95% confidence intervals. Additionally, a margin of error of 3% is usually desired. How many people should be surveyed? We're given that the margin of error equals 0.03, and since we're working with a 95% confidence interval, z star is equal to 1.96. We don't have any information from a previous study, so we're going to use our second option and set p-hat equal to 0.5. Plugging in our formula, we find 1,067.11, but since we can't take 0.11 of a person, we round this up and say that we need 1,068 people. On the next page, we have several examples for you to try. For each of the problems, try to mimic one of these two examples. Pause the video, see how far you can get, and when you come back, we'll look how to solve them together. A study at the Harvard School of Public Health found that 44% of 10,000 sample college students were binge drinkers. A student at the University of Minnesota plans to estimate the proportion of college students at that school who are binge drinkers. A. How large a random sample would she need to estimate it within 0.05 with 95% confidence if she uses the Harvard results as a guideline? So notice from a previous study, we have that p-hat is equal to 0.44. Also, since we're going to work with 95% confidence, we know that z star is equal to 1.96. And again, you can find that value on page 13 of your notes. And then they tell us that the margin of error is equal to 0.05. So now we can plug this into our formula. First, I'm going to write down the formula. And now plugging in all the values. Placing this in the calculator gives us which says we need a sample of at least 379. Part B asks, how large a sample would she need if she wanted to estimate with 99% confidence, leaving all other parameters of the experiment the same? How does this compare with the needed sample size in Part A? So notice here, the only thing we're going to change is z star is now going to be equal to 2.576. So again, writing down my formula. And now I'm going to plug in all my values. This gives us which suggests that we need a sample of at least 655. So notice that our sample size from Part A to Part B became larger. So this tells us as confidence increases, so does the sample size. Part B. Suppose that a student at the University of Miami wants to estimate the proportion of college students at that school who are binge drinkers with 0.05 with 95% confidence. This student is not aware of the studies at the above schools and therefore has no prior results to make a guess based on prior studies. How large a sample will he need? How does this compare to the needed sample in Part A? So notice here, since we don't have any information from a previous study, we have to use the other way to estimate p hat, and so we'll set p hat equal to 0.5. And so this is coming from the previous page where we say how do we get our estimate of p hat, and we have one of these two options. So writing down our formula, notice that everything else is going to stay the same as it was in Part A. Plugging in our values. And then placing that in the calculator. So we need a sample of at least 385. So notice the only difference between Part A and Part B was whether we used information from a previous study or we used the other method of guessing p hat to be 0.5. Notice when we had information from a previous study, the sample size was smaller when we had to use the 0.5. 0.5, keeping everything else the same, will always result in a larger sample size compared to using information from a previous study. So this is why if we have information from a previous study that's reliable, we do want to use it for our sample size calculations. In these problems, we looked at sample size calculations for a single proportion. Now we'll look at sample size calculations for a single mean. Recall that when working with a single mean, we have this formula for the margin of error. Solving for n yields this formula. But there's two problems with the formula. One, since our goal is to find sample size, there's no way to find t star because we don't know the sample size yet. Also, we can't find s since we don't have sample data yet. So instead, we're going to replace the t star with z star. Again, we're always going to round end up to the nearest whole number to find the minimum sample size required. If we compute n and come up with a small sample size, we should go back and be more demanding of either having a smaller margin of error or a higher level of confidence. So this sigma tilde right here, that's the piece we haven't talked about that. This is our estimate of standard deviation. And so how do we get that sigma tilde? Well, there's 4 different ways we can estimate its value. Similar to before, we can use data from a previous study or a similar population. We could take a small pre-sample to estimate S. We could use it by taking the range, which is the max minus the min, of possible values, and then divide that range by 6. And again, that's being that's coming or motivated by the empirical rule. Or we could just make a reasonable guess. So if we already knew something about the data and we had a reasonable guess, we could use it. So let's look at 2 different examples. Suppose we want to estimate the average GPA EKU, where GPAs go from 0 to 4, with a margin of error of 0.1, 95% confidence. How large a sample do we need? So we're given that the margin of error is equal to 0.1. Also, z star equals 1.96 since we want a 95% confidence interval. The GPAs range from 0 to 4. So we can estimate our standard deviation by using the range divided by 6. Therefore, our estimate of standard deviation will be 0.6667. Filling in the formula, we have the following. And so notice this suggests we would need a sample size of at least 171. Let's look at another example. Again, suppose we want to estimate the average GPA at EKU with a margin of error of 0.1 with 95% confidence. A previous study found the standard deviation of a similar college to be 0.27. How large a sample do we need? We are given that the margin of error equals 0.1. Also, z star still equals 1.96 because we're looking at 95% confidence. The previous study found the standard deviation at a similar college was 0.27. So we're going to use that 0.27 to estimate our sigma. So sigma tilde will be equal to 0.27. Filling in our formula. So now we only need a sample size of at least, and really we should have at least in here, 29. This sample size is smaller than the sample size requirement of 30. So we should go back and be more demanding by either having a smaller margin of error or a higher level of confidence. On the next page are two examples just like these. Take a moment, pause the video, and see if you can work those two by mimicking the problems on this page. When you come back, we'll go through the answers together. All right, let's look at these. A tax assessor wants to estimate the mean property tax bill for all homeowners in Madison, Wisconsin. A survey 10 years ago found a sample mean of 1,400 and a standard deviation of 1,000. Part A. How many tax records should the tax assessor randomly sample for a 95% confidence interval for the mean to have a margin of error equal to 100? Alright, so we're going to figure out how many tax records should we randomly sample from. So let's identify a couple different pieces here. So first of all, notice we're working with 95% confidence. So our z star is going to be equal to 1.96. Our margin of error is going to be equal to 100. And then the other piece we're going to need is our guess at our standard deviation. So notice we've got a survey from 10 years ago that found a sample mean of 1,400 and a standard deviation of 1,000. So we're going to use that previous information to get our guess of sigma, or pardon me, of our standard deviation. So writing down our formula. And now we're going to plug in each of our values. So we need a sample of at least 385 records. I'm missing my R there. There we go. B, suppose the assessor is willing to decrease the confidence to 90% to save money collecting the information. What sample size would he need? So now the only thing that's going to change is our z star. And remember that we can turn back to page 13 in our notes to find those common values for z star. So here, our z star for 90% is 1.645. So again, writing down our formula. Plugging in the values. So we'll place this in our calculator, giving this value. Rounding up, this says we need a sample size of at least 271. Alright, so the last bit in this section talks about confidence intervals with a proportion from small sample sizes. I'm going to leave you to read that on your own from your textbook, located on in My Labs on Blackboard. And then the last page of the notes has just some additional confidence interval examples, one for a single proportion and one for a single mean. Each of those have corresponding videos that go along with them. One thing to note is for the video for the single proportion, I had made this video for a different class. So the sample size requirement on it, I do believe is 10 instead of 15. Just know that for your class, we are using that requirement of 15. Or pardon me, of 10. Goodness, I am so sorry. Your class uses the requirement of 15. And this ends the chapter 8 notes.